All right, so this next problem is going to be the Gram-Schmidt process. Okay. So for the Gram-Schmidt process of finding an orthogonal basis for the column space of this, the very first thing you do is you just say, I'm going to let U1 equal V1. And then V2 will equal U2 minus the projection of U2 upon V1, which will equal U2, which is 1, 1, and 0. Now we're projecting onto V1, so there's going to be a lot of V1s. So that's going to be 1, 1, 0. And then dotted with V1, which we chose to be U1. Okay. Okay, so the projection of U2 upon V1, that's what we're having to consider at this point. That would equal now 1, 1, 0, and minus, okay, so this one right here would just turn out to be a 1. And then 1, 0, and 1, okay. So 1 minus 1 half would be 1 half. 1 minus 0 would be 1, and that would turn that into a negative 1 half. Okay. And the first thing you want to ask yourself is, when you get to this part of the problem, first of all, is V2 really orthogonal to V1? Well, all right, this is V2 right here. So if I do the dot product with the V1 that I created, I'm going to get a 1 half and a negative 1 half. They cancel each other out. And so, yeah, they are really orthogonal to each other. Okay. Now we have to find the third orthogonal vector, V3. And I'm going to have to zoom out a little bit on this one because it's a bit longer of a problem. Oh, wrong way. All right. V3 is going to equal U3 minus the projection of U3 upon V1 and minus the projection of U3 upon V2. And so my U3, where'd you go? Was 0, 1, 1. So this is going to turn into 0, 1, 1. Okay. Minus the projection of U3 upon V1. So that would be 0, 1, 1. All right, dotted with V1, which is 1, 0, 1. Okay, and then 1, 0, 1. Remember, when you're projecting onto a vector, there's going to be a lot of dot vector involved. All right? And then minus, this is 0, 1, 1. And then dotted with, okay, where's my V2? One half, 1, and then negative 1 half, and then multiply by, this is where we end up getting into a lot of the fractions. Okay. So, this would become, you just see that guy alone right there? That's 0, 1, 1. That'd be 1 divided by 2. Okay. So what's going to appear on the top of this fraction? We're going to have a positive 1 and a negative 1 half. So a positive 1 and a negative 1 half would give us a positive 1 half. All right. Now 1 half times 1 half is 1/4. Negative 1 half times negative 1 half is also 1/4. Add those together, you get 1 half. And then 1 half plus 1 is really 3 halves. And then that's going to become, well, that's not going to change. 1 half 1 and negative 1 half. Okay, so that would become 0, 1, 1. And then minus, let's put it like this. All right, so that would turn into 1/3. So 1 half times 1/3 is 1/6. This becomes 1/3. And negative 1 divided by 6. Okay, let's do the first one, these two first. So 0 minus 1 half would turn into a negative 1 divided by 2, and that would be a 1, and 1 minus 1 half would be 1 half. And then minus, and this becomes 1/6, 1/3, and negative 1 divided by 6. Okay. Now, negative half minus 1/6. You can think of this as negative 3/6 minus 1/6, which would be, you know what, let's do it in a couple steps. Negative 4 divided by 6. Now 1 minus 1/3 would be 2/3. And 1 half plus 1/6 would be 3/6 plus 1/6 would be 4/6. Okay. And to simplify that out, that would become negative 2/3, 2/3, and 2/3. Okay. Now we need to look at our problem and see, does this make sense? Okay. Well, first, let's have a look at 101. Okay. So now if I do the dot product with my V1, which is 101, I get negative 2/3, and I get a positive 2/3. So they cancel each other out. Okay. And now if I look at V2, now is V2 orthogonal to this vector right here? We're just checking for orthogonal, being orthogonal at this point. And so 1/2 times negative 2/3 would be a negative 1/3. Negative 1/2 times 2/3 would be a negative 1/3, and then 1 times 2/3 is a positive 2/3. So yes, they do in fact end up canceling each other out, and we did end up with an orthogonal basis.